Hey there guys and girls, Mr. Marek again with more electricity fun. In this video, we're going to learn about electric potential energy. Remember that the term potential energy, which generally we give the symbol U, refers to the energy due to the configuration or position of a system of objects, keyword there being system. So, a couple of examples. You are in the Earth's gravitational field. Therefore, you have gravitational potential energy. Now, sometimes, probably not often, you stand next to a giant spring that's like compressed. Therefore, you have elastic potential energy. Pretty rare for you, but it can happen. Now, two charges which are close to each other, like a proton next to a big positive charge, would have electric potential energy. So all three of these situations, the object, in this case U, in this case U, in this case the proton, have energy due to their position. So the symbol we give, gravitational potential energy, is U subscript G. Elastic potential energy, we typically do U subscript S, S for like a spring. And then electric potential energy, we typically do U with the subscript E. So all those things have potential energy due to their position. So a little bit more about this electric potential energy thing. Electric potential energy is going to exist when you have a charge in an electric field. So any charge in an electric field will have electric potential energy due to its position in that field. The way that we would define the system typically is the charge that we're interested in, and then the electric field or the thing that causes the electric field, however you kind of define it or think about it. A really important note is that we define the electric potential energy to be zero when the distance between the charge we care about and whatever is creating the electric field, so the two charges basically, whenever that distance is infinity. Now, infinity is kind of a tricky term. I'm going to kind of define it as being so far apart that they don't really affect each other. That's what infinity means for us. So, let's think about the sign of electric potential energy. Here we've got two charges, one big, one small, and they are initially far apart, which means that the separation between them is infinity. Let's suppose we keep this guy fixed in place, so it's like held by something. So the question is, what do we have to do to move the smaller charge closer to the big charge? Remembering that positive charges will repel each other, the answer is we would have to push it. And so if we're going to push it and make it move, that means that we're going to be doing work on it. We push it to make it move, therefore work is done. So whatever force we exert times that distance will give us the work, which gives us the change in energy, just like always. The thing is that since the force depends on the distance as well, the force is changing. So we really can't do force times distance to figure out how much work is done on that charge. So since we had to do work on the charge is going to gain some potential energy, hence electric potential energy. So it's got more electric potential energy than it did before we pushed it. So if we do one of these diagrams, we're going to call these LOL diagrams or energy bar charts, the system would consist of the two charges. And I'm going to say that state 1 was the original when they're far apart. State 2 is when we push the small one closer to the big one. In state 1, the energy is equal to 0. So on the bar chart on the left, we wouldn't draw anything. Then we did some work, which means the energy changed, and doing that work caused potential energy to change, and so now on the right-hand bar chart, we would have some electrical potential energy. If we were to let go of that charge, it would move on its own to the right, so it would get pushed away by the bigger positive charge, and so it would gain kinetic energy and start to move. And so in that third picture, I'm going to have a decreasing potential energy, but an increasing kinetic energy. Let's look at another example. Suppose that we have these two charges, which are initially far apart. So notice that they are opposite charges, positive and negative. Remember that positive and negative charges are going to attract each other. And again, we're going to hold the bigger one in place. So the question that I have now is, what do you have to do to move that negative charge to the left, get it closer to the positive charge? Well, the answer is nothing. A negative charge will, if it's free to move towards a positive charge. They attract each other. And so at some time later on, the negative charge will be moving towards the positive charge, and it'll be going faster. It'll be speeding up, gaining kinetic energy. Now, as it moves towards that positive charge, it has to be losing electric potential energy because it's gaining kinetic energy. So, you might be thinking that since the charge has to start with zero energy, something's going on, something's amiss. So the charge does start with zero potential energy because it started at infinity. That's by our definitions and our conventions. So that is a true statement. Its original position, the electric potential energy is zero. But I said over here that it is losing potential energy because it is gaining kinetic energy, which is also a true statement. So the nitty-gritty of this is that its potential energy is becoming more negative. It's losing energy starting from zero, which means the potential energy is becoming more negative. Let that kind of sink in for just a second. So at this position right here, the kinetic energy is like 500 joules. The potential energy is like negative 500 joules. Now don't write all this down, but let's just kind of talk our way through this for just a second. Energy can be negative. We've always avoided the situation by choosing our coordinate system correctly and our setting 0 to be in a convenient spot, but now we can't avoid that anymore. The reason we can't avoid that is because we have two kinds of charge. We have the positive, negative, so we have two different kinds of interactions. And so there's no real way for us to avoid the possibility of having negative energy. So, could the other kinds of energy that we've already learned about also be negative? And the answer is yes, but only potential energies. Kinetic energies are always going to be positive. But gravitational potential energy could be negative. So suppose that we're back in AP Physics 1, and we're doing that thing where we rolled a marble down a ramp and we predicted how far away it would land. When we did that, what we basically did was we set the bottom of the ramp equal to a height of 0. And so if our marble started with 10 joules of energy at the top of the ramp, it would have 0 joules of energy, potential energy, at the bottom of the ramp. Well, if we consider the fact that it's still going to go down and hit the floor, if we measured its energy at the floor, we would have to assign it a negative value. So maybe the potential energy just before it hits the ground would be like negative 20 joules. Regardless of where we set this, we would always get the same answers to our questions because the important thing is the change. And so in this particular situation, regardless of how you set it up, you would still get the potential energy change for that marble to be negative 30 joules. It would lose 30 joules of energy, and that's the important number. Same thing with electric potential energy. It's the change that's most important. So don't be too worried about the fact that the energy is negative. It's going to happen. We're going to have to deal with it. So back to our regularly scheduled example. So here's the system, before and after. Let's draw an LOL chart, but this time let's include negative for our energies. Initially, the energy of my system is 0. It's infinitely far away and it's not moving. As it moves closer, we lose electrical potential energy, so that's going to go into the negative, and we gain kinetic energy, so that goes up in the positive. So if we look at that graph down here, the total energy of the system is still 0. Just like it was over here. So, let's kind of sketch out how energy changes with distance. There's two situations. We could have two like charges, whereas we decrease the distance between them, the electric potential energy becomes more positive. Or we could have the situation where the charges are opposite, in which case decreasing the distance makes the potential energy more negative. So we're just going to graph the potential energy versus the distance between the charges. For two like charges, the energy is going to be positive. So if they have 0 separation, potential energy will be infinity, and when they're very, very far apart, the potential energy will be 0. For two opposite charges, when they are not separated by any distance, the energy would be negative infinity. And then as the distance goes and gets far, far apart, then the energy goes to 0. So we kind of talked about the sign and the basic concept, and remember that energy is still conserved in all these examples. So how do we figure out the size of the potential energy? Well, we have a real simple equation. Potential energy is equal to kq1 q2 over r. Notice that it's r, not r squared. Otherwise, it would be a force. And then our convention is that the potential energy is 0 when r is 0. Or excuse me. That should have been infinity. I wrote 0, I meant infinity. Now again, what's really important is the change in potential energy. That's what's going to tell us how fast things are moving and how much work is needed. And so the change in potential energy, just subtract the two values using that relationship. And so final R minus initial R would be the only difference. And so since the R is changing would be the only difference, it would usually be easy. It's just to factor out the K, Q1, Q2 thing. And that way you don't have to do all that plug and chug twice. You can just do it once, and then all you have to do is find the difference in 1 over R, basically. Now a big difference between this unit and the previous unit. In this unit, when we have scalars like energy and later on voltage, we're going to use the sign of the charge when we substitute in for Q. So if Q is negative, we're going to put a negative sign in there in the equation. And that's going to give us the correct sign for the energy. So that's kind of a departure from the last unit, which everything was vectors. In this unit, everything's scalars. So we're going to put in the signs for the charges so we get the correct sign out for the energy. So let's look at a quick example. Suppose we got a big positive 5 coulomb charge which we're going to hold at rest. And then we take a sphere that's got a mass of half a kilogram and 5 microcoulombs of charge, and we put it 2 meters to the right. We let go of it. We want to know what its velocity is after it's moved for 1 meter. So there's the big plus 5 coulomb charge. There's the other charge. When we let it go, since positives repel, it's going to move to the right. we're looking for how fast it's going, after it's moved 1 meter, and its initial separation was 2 meters. So we go from 2 meters to 3 meters. If we sketch out a quick LOL chart, system is those two charges. We're going to start with a bunch of potential energy, and then as it moves, it's going to lose potential energy and gain kinetic energy. Since energy is conserved, then whatever potential energy is lost has to equal the kinetic energy that's gained. To kind of write it in equation form, we're going to lose some potential energy. That's going to tell us how much energy is gained in kinetic energy. Okay, so let's find the change in potential energy. I'm going to kind of use this way just because I don't want to do all the arithmetic. Factoring out the K, Q1, Q2 would look like that. That is what I was trying to say. And then 1 over R minus 1 over R initial would look like 1 over 3 minus 1 over 2. So do the multiplying. You would get 225,000. Coulombs would all cancel out, so that would be Newton times meter squared. And then 1 over 3 minus 1 over 2 would be negative 1 over 6. And the negative sign shouldn't surprise you because this thing is losing potential energy. We should get a negative sign for our answer. So if you divide 225,000 by 6, you get something like 37,500. One of those meters cancels out with the meter next to the 6, because one's on top of the fraction, one's on bottom, leaving us with Newton times meter. And then a negative times a positive gives you a negative. And so remember, a Newton times a meter is a joule. So this sphere has lost 37,500 joules of energy, which is going to be equal to the gain of the kinetic energy. So since it started with no kinetic energy, now it's got 37,500 joules of kinetic energy. And so solving our kinetic energy equation for velocity real quick, something we should definitely be able to do, that would give us something like 387 meters per second, so faster than the speed of sound, basically. And don't forget the direction, it's moving to the right. So, kind of a tricky question here. Suppose we took the big charge and we made it negative 5 coulombs instead. Question here is, what would change? Kind of think about that for a second. What's going to change? If you said it's going to go the other way, you're partially correct. That thing's also going to be going faster. By decreasing the distance instead of increasing, we're going to get a bigger change in energy. So if I take that potential energy change equation that we just started with, the initial position is still 2 meters. Now I'm going to make that a negative 5 coulombs. And then instead of 3 meters, we're moving to the left. We're getting closer to the big charge. So I'm going to make that 1 meter. And so that's going to give me a bigger energy change. It's still negative because I've got two opposite charges now. It's going closer, it's losing energy, but it's getting more negative. And so now the K is going to be larger. And so again, finding my velocity from my kinetic energy, now we would get something like 671 meters per second. That's because it's moving to the left. So, easy example, right? So this whole electric potential energy thing can get kind of confusing because of the whole negative energy thing. So the thing to remember is when you're working with the equation, plug in the signs for the actual charge. We didn't do that in our previous unit because everything was vectors. We had to consider the direction. Remember, energy is a scalar. It doesn't have a direction. And so that's going to be a little bit confusing, and so that's kind of something to make sure that you focus on. Of course, we'll be doing some practice next time in class. I think we've gone on long enough here today. I will see you next time. Ta-ta.